Welcome back to our online classes, and in today's class we are going to look at different types of unit cells which are found within the solids. And we know that solids can be classified based on the way the atoms are arranged, and this can give us amorphous solids in which the atoms are not arranged in a proper way, and crystalline solids in which the atoms are arranged in a proper way. In these crystalline solids we can have a symmetrical three-dimensionals of the atoms, and this is what we call crystal lattice. In crystal lattice we can have a smallest portion which is repeating themselves, and this is what we call a unit cell. In this video we are going to look at different types of unit cells like simple cube, face-centered cube, body-centered cube, and atomic packing factor. So the first one we are going to look at simple cube. Now let's start by looking by what we call atomic packing factor. What is atomic packing factor? Atomic packing factor is the ratio of the volume of the atoms in a unit cell divided by the entire volume of the unit cell. Now we can say that atomic packing factor is the volume of the atoms in the unit cell divided by the volume of the entire unit cell. However, in each and every unit cell, there's what we call the effective number, and this effective number is different from every type of a unit cell, and this one we can represent it by Z. Now, once we have the atomic packing factor, we can have what is called atomic packing efficiency, which is the atomic packing factor times 100%. Times 100%. Okay, now once we have the atomic packing factor, it can then tell us how many or how much of that volume is occupied by the atoms and what is the free space which is void in that space. Okay, so let's start by looking at the cube. Let's look at this cube. So this is the cube that we have. For example, so in the simple cube we have 8 atoms at each corner. So we're going to have atom here, we have atom, we have in each corner there's one atom represented. Okay, so there's a total of 8 atoms. Now we are going to look with this Z. The Z gives us the number of effective atoms, and the number of effective atoms can be determined by looking at the number of atoms that are contributed by the corner atoms. Now the number of corner atoms or the corner atoms contribute to 1/8 of the total number of the atoms in the cube. And how many atoms are in this cube? There are 8. 1, 2, 3, 4, 5, 6, 7, 8. So we multiply by 8 to know that how many atoms, effective atoms, that are contributed by a corner. So 1, 1, and this gives us a Z value, which is Z is equal to 1. So it tells us that in the simple cube the effective number of atoms is 1. Now we can then look at the volume of the sphere. Now atom looks like this. It can look like a sphere, and the volume of a sphere is given by 4/3 pi r cube. So we can then say here we have 4 pi r cube times 1, which is Z. The volume of the unit cell is given by VC is given by A cube, and then we have to ask ourselves what is A. Now in this case we are going to take one face of the cube, and how many faces are here? There are 4. There are 6 faces: the one facing me, the one facing at the back, the one at the right, left, up, and bottom. So there are 6 faces. If I was to draw the front face like this, okay, we have 4 atoms at this corner, so we have 4 atoms. And in the simple cube, the 4 atoms like this. Okay, So you can see this is the front face that is facing us, and you can see the distance between here and this part is the length. So this is what we call the edge length A. Now if you look at these atoms, it have a diameter. From this point to this point is a diameter. However, this face touches half of it, like from this part until this part, and half of a diameter is a radius, so we are going to have R at this point. And also, okay, this is not perfectly drawn, but here is a radius and this side is also a radius. So from this point to this point is also a radius. So you can see that the edge length A is in this case is 1R plus another R, which is going to give us 2R. So in simple cube, our edge length is given by 2R. Okay, and the volume of the unit cell is equal to a cube, and this is going to give us 2R cube. 2R cube is going to give us 8R cube. So it tells us that the VC, or the volume of the unit cell in simple cube, is 8R cube. So we can then proceed and calculate our atomic packing factor by saying atomic packing factor is equal to 1 times 4 over 3 pi R cube. This is the numerator part, divided by 8R cube, and this is going to give us 4 over 3 pi R cube over 8R cube. R cube cancel R cube, and this one is going to give us, let's punch from the calculator, it gives us a value of 0.52. So atomic packing factor for simple cube is 0.52. So it tells us that out of 1, 0.52 of the entire volume is occupied by the atoms. So if we subtract 0.52 from 1, we are going to get 0.48. So it tells us that 0.48 of the entire volume is unoccupied by the atoms, and this gives us what we call the void volume. Now, we did talk about atomic packing efficiency. Atomic packing efficiency still tells us what percent of the entire volume is occupied by the atoms. And we said atomic packing efficiency is equal to atomic packing factor times 100%. And therefore, in this case, we have 0.52 times 100%, and that's going to give us 52%. So it tells us that the atomic packing efficiency of simple cube of a unit cell is 52%. So 52% of the entire volume is occupied by the atoms, leaving 48% unoccupied. There's what we call the coordination number. A coordination number is the number of the neighboring atoms in a unit cell. So I'm gonna rub here and see what's the coordination number of simple cube. So we are going to let's take an example of this atom at the corner. If you look at this atom, we're saying that the coordination number Cn is the number of the neighboring atoms in a unit cell. So this is our unit cell, and if we were to take this atom at the corner, it is being neighbored by this atom here at this edge length. It is also bordered with this atom here in this edge length, and is also bordered with this atom here in this edge length. Because this is a unit cell, there's also another unit cells on the other side, and this atom then on the left hand side will be bordered by another atom of the same distance like this atom, and this is going to give us A. And this atom here will also have another atom on the back side bordering this atom, and this is going to give us another atom here of the same edge length like this, and this atom down here of this edge length is going to give us another atom on top here of the same edge length. So let's look, if we are to consider these atom, how many atoms are neighboring this atom here? So we have 1, 2, 3, 4, 5, and 6. So it tells us that the coordination number of atoms in the simple cube is 6. So we're going to say coordination number is 6 in the simple cube. So that's all we need to know about the simple cube. So let's look at the second one, or face-centered cube. Now, the same in the face-centered cube, we're going to look at atomic packing factor, which we have seen is the Z times volume of the atoms divided by the volume of the unit cell. So still we can draw a cube. We can draw a cube. So this is a cube, and this cube has how many atoms? It has 8 atoms as usual. 2, 3, 4, 5, 6, 7, 8. So let's look at the effective number of atoms Z. Just like we said that every corner atom will contribute to 1/8 times the total number of the atoms, which is 8. So this is going to give us 1. However, in F.C.C, there are 6 atoms in the total phase, meaning that in each phase there's 1 atom present. So I'll use this ink to give the number of atoms present in each phase. So this one, the atom at the face facing down, and this one here is the face facing the front face, and this one is the one on the left, and this one is the one on the right, and this one is the one facing up, okay, and this one here is the one behind. So how many faces we have here? 1, 2, 3, 4, 5, 6. So we have 6 atoms, 1 in each face. Now, 1 atom is being shared by 2 faces on the opposite side. So if I have one face facing me, on the other unit cell, there's also that atom is also being shared with that face. So meaning that in F.C.C, we have a half of the, because 1 atom is shared by 2 faces, so it gives us that it contributes to a half of the total number of the atoms in the faces. And how many atoms are there? There are 6 atoms. So it tells us that in F.C.C we have a total number of 3 atoms contributed by the 6 faces. This makes our Z, the effective number of atoms in F.C.C, to be 1, the 1 contributed by the corner atom, plus 3, which is contributed by the 6 faces, and this gives us to a total of 4 atoms. So the effective number of atoms in F.C.C is 4 atoms. Let's look at them. We said VC is equal to A cube, and therefore let's look at the edge length. Now, if I extract, also remove one face of this cube, I'm going to have something like this. Okay, now this one atom, this one atom, this another atom, and this also another atom. In F.C.C, these atoms at the corners does not touch each other, unlike the one we saw in the simple cube. And this is one phase, and in one phase there's one atom present, and this atom present touches the 4 atoms. Okay, so as you can see that none of the 4 atoms, or 2 atoms on each edge length, does not touch each other, and therefore we cannot say that our edge length is R and R in this case, because these 2 atoms does not touch each other. So we can then join this one, because there's a relationship between this atom and this atom, because there's one atom at the center which is uniting them. As usual, this is half of the diameter, so this is R, this is R. This is a diameter, so it's going to have 2R, which is the same as R1 and R2, and also this one, yes, it's not perfectly drawn, but this is also R. So how many R's are here? So we have 4 R. So if this is my A, B, and C, and this is edge length A, and this is another edge length, then we can say then AC squared is equal to AB squared plus BC squared from Pythagoras, right? AC squared is 4R, that is 4R, and AB squared is A squared plus B squared is also A squared. So this gives us a value of 4R is equal to 2A squared, and when we do mathematics, this will give us, or if we go further, we can square everything, but at the end it's going to give us A is equal to 2 root 2R. If we divide both sides by 2, and then we have the squared here, we do away with it and give us the edge length in F.C.C is 2 root 2R, okay, which is still as like a root 8R. So now we can then say that our edge length here is 2 root 2R, and what is VC? VC is equal to A cube, and we can cube this, to give us, so we have 2 root 2 cube, and this gives us 16 root 2, and this is going to give us, when you cube this to get VC, which is that one cube, we are going to get 16 root 2 R cube. So we can then substitute in this to get the atomic packing factor, and in this case our Z is 4, so we're going to have to say 4 times 4 over 3 pi R cube over 16 root 2 R cube. This R cube cancel R cube, and this one is going to give us, let me wrap this point, and this one is going to give us a value of, this is F.C.C, so that's going to give us a value of 4 times this one, it gives us 0.4. It's going to give us 0.74. So the atomic packing factor for F.C.C is 0.74. So it tells us that 0.74 of the entire volume of the cube or of the unit cell is occupied by the atoms, leaving 1 minus this one is 0.26, leaving 0.26 of the entire volume is unoccupied. So if we are to look at the atomic packing efficiency, then it's going to be 0.74 times 100%, which is going to give us 74%. So it tells us that in F.C.C there are a lot of atoms which are occupying the volume, unlike in simple cube. So this tells us that in F.C.C there's high packing, unlike in CF. So let's look at the coordination number of this unit cell. So I'll wrap to create a space so that I can draw it in another one. So we had said that, okay, so let's draw so we have our atom here 1, 2, 3, 4, 5, 6, 7, and 8. And we did say that in each phase there's one atom. So in this phase I'll put this one, and in this phase I'll put the downer part, I'll put this one here, and this one I'll put red, the left hand side, and on the top I'll put it here, and at the back I'll put it somewhere here, and in front I'll put this one here. So we also have, so how many? 1 2 3 4 5 6. So we have 6 atoms, one in each phase. So as you can see that this atom, then we can use it to show the relationship between these atoms and the neighboring atoms. So in this case we are looking at the coordination number. If you look at this atom, it is neighboring, it is neighbored by this. So 1 2 3 and 4. So there are 4 atoms already neighboring this. However, if you look at these atoms on the edges, they are closer to this compared to the one at the lower face. So this one is very far, and therefore the one neighboring this are these atoms in space. Okay, these 4 atoms, and then we can then link them to this atom. We can link them to this. We can link them to this. So how many atoms are neighboring this already? 1 2 3 4 5 6 7 8. There are 8 atoms neighboring this atom at the center already. However, if you look at these 4 atoms, they have also other atoms on the upper space, and that one can make us then to extend this, okay, so that we can have another unit cell on top, and these 4 atoms here will still appear on this face 1 for this one, and this one will still appear here 2, and the one at the back will still appear, put it there, and the one on the face facing me, I'll put it here. So you can see that there's still these 4 atoms are linked together, and they are closer to this atom. So this is 1. We remember we already have 8 atoms neighboring this, so this one will be 9, this is 10, and this is 11, and this is 12. So it tells us that the coordination number in F.C.C is equal to 12. So this is how you can determine the coordination number of F.C.C in, how you can determine the coordination number of F.C.C in a unit cell by just drawing. Remember, coordination number is the number of the neighboring atoms. Now let's look at B.C.C. B.C.C. So our third one is B.C.C. Now in B.C.C, we're still going to look at atomic packing factor, which is Z times Vs over Vc, and let's draw and see how it looks like. This is our cube. So there are 8 atoms, 1 in each corner. So we can look at Z is equal to how many? We're going to see the effective number of atoms in B.C.C. In simple cube, we saw it was 1. In F.C.C, we saw it was 4. And now we can see here. However, we realize that when it comes to B.C.C, there's 1 atom at the center, okay? There's 1 atom at the center. So then we can proceed and say the corner atoms contributes to 1 over 8 times 8 atoms, and that's going to give us 1. And if you see that this atom is at the center, so we're going to have BC atom contributes to 1, and that's going to give us 1 plus 1 is going to 2. So Z is equal to 2 in this case. So Z is equal to 2. Let's take then look at the edge length. A is equal to what? I'll take one face, so I'll draw one face like this, but you realize that this is what we have, okay? It is different like in F.C.C and also in a simple cube. B.C.C is a little bit tricky because one atom is shared by the 4 atoms on the top and also another face at the bottom. If we are to bring another face on the top, they are still going to share this atom on the top, and therefore we can then relate this atom at the center to this atom on the other side diagonally, because there's no relationship between these atoms. This one is no. This atom can relate this or can relate this. So if you were to name here A, B, C, D, and then we can have this one, this guy's here. Okay, so this is what we're looking for. Now, in another word, we can then say AD squared is equal to AD squared, and in AD squared, remember we have this one at A, we have this one at the center, and we have this one at D. So the radius starts from here, so we have R, 2R, and another R. Remember the 2 atoms, this one, we are relating this because one face is on the top, and that's what relates them together. So meaning that our AD here is equal to 4R. So our AD is equal to 4R. Now from the F.C.C we did see this one is root 2, and so this is our A. So we can say AD squared is equal to AC squared plus CD squared, and AD squared, so this will leave AD to be the root of AC and CD, and AD is equal to 4R, and AC squared, AC we have found to be root 2A plus, this is root 2A plus CD is equal to A, and this can give us, I'll rub here. And this is gonna give us 4R is equal to root 3A. To get A, we can divide both sides by root 3, so that our A is equal to 4R over root 3. From here, we can substitute and calculate our A.P.F. And if you calculate our A.P.F, you're gonna say A.P.F is the atomic packing factor is equal to Z, which is 2 times 4 over 3 pi R cube over our edge length is 4R over root 3, and our VC is going to be, so our VC is equal to A cube, and this is going to give us 4R root 3 cube. So this R cube will cancel this R cube and this one. So meaning that A.P.F is going to give us 8 over 3 pi R cube divided by 64 root 3 over 9 R cube. This R cube will cancel this cube, and if you have 8 over 3 pi, okay, divided by answer, it gives us 0.68. So our A.P.F, atomic packing factor, is equal to 0.68. So it tells us that out of the entire volume, 0.68 of the volume is occupied by the atoms, leaving 0.32 volume of the unit cell to be unoccupied. And therefore, if we're looking at atomic packing efficiency, then it's going to be 0.68 times 100%, and that's going to give us 68%. So that's the atomic packing efficiency of B.C.C, which is 68. So let's look at the coordination number. In this case, just allow me to draw it so that it can be a little bit nicer. So the coordination number in this case, so we have 1, 2, 3, 4, 5, 6, 7, 8, and we did say that with B.C.C there's one atom at the center. Okay, just this one is not in the top, it's inside. So because it's inside, it's neighbored by this 1, 2, 3, 4, 5, 6, 7, 8. So the coordination number of B.C.C is 8. So this marks the end of this, and then we can make a summary. We can make a summary of this by saying that we can make a summary of what you have learned today by looking at this table. Okay, we can then say we have F.C.C. Let me start by simple cube, F.C.C, F.C.C, and B.C.C. So atomic packing factor here is 0.52, and here is 0.74, and in B.C.C it is 0.68. Okay, and atomic packing efficiency is 52% for F.C.C. F.C.C it is 74%, and it is 68. And Z, which is the number of effective atoms, here we have 1, F.C.C we found 4, and in B.C.C we add 2. And then coordination number for this one, S.C, we found to be 6, F.C.C we found 12, and B.C we found 8. So this is what you need to know. Thank you so much for watching, and I hope we tried to elaborate, and therefore if any question, something that you're trying to understand much better, you can ask in the comments, and for HCP we're gonna look it in the next video because of the time. Thank you so much for watching. Welcome. Hey, remember to subscribe if you have not subscribed. Subscribe and like the video, share it with your friends, so that if you subscribe when you post such things, and then you come and watch, you get notified. Thank you so much as you prepare for your next test and exam. Goodbye.